Let's do a couple more examples of complex fractions, which is when fractions are inside of other fractions. Because there's a subtraction on both the top and the bottom, we can't just multiply by the reciprocal in this method. So we're going to use the LCD method, which is when we multiply all numerators in the top and the bottom by the LCD, which is the least common denominator. So what that means is we look at all the bottoms of the fractions and we're figuring out what can we multiply by to get them both to cancel. And if I multiply by x squared, and I'm gonna maybe write it even x squared over 1, just to have that idea that I'm multiplying the tops, well then the x squareds will definitely cancel, and x squared divided by x is also gonna cancel. But we have to remember, it's not just the fractions we're multiplying, it's every term on both the top and the bottom. And if it helps, you can put the 2 over 1 and the 4 over 1 to remind yourself that we're multiplying all numerators, and that includes these whole numbers too. So I'm gonna write this one out in detail, just so we get the idea that I'm multiplying the 2 by x squared, and the x squared by 1 over x, so that's gonna be x squared over x. All right, so I multiplied top of the fraction by x squared, top of the fraction by x squared. Same on the bottom, top of the fraction by x squared. So that's 4x squared minus x squared over x squared. And the reason we did this is to get these fractions to cancel. So x squared divided by x squared, well, that's just 1. Make sure you don't just cross it out and then there's nothing left, right? When we cancel a fraction, there's still a 1 left because any number divided by itself is 1. And on the top, x squared divided by x, well, that's just x. So let me rewrite it simplified now. So the top will be 2x squared minus x, and the bottom will be 4x squared minus 1. All right, so we multiplied all numerators, the tops of the fractions, by the LCD, so that the fractions would go away. So now this is not a complex fraction. It's just a rational expression, one polynomial divided by another. So now it's time to simplify. It is not time to cancel though, right? And a common mistake is to start crossing stuff out. We can't do that yet. We need to simplify and factor both the numerator and the denominator. So if there were like terms, we would want to add or subtract them, but these aren't like terms because this has a squared, that doesn't, this has a squared, that doesn't even have an x on there. So there's no like terms, but I can definitely factor. So let's do that. The top has a GCF. Both terms have an x, so I need to divide by x, so I get 2x minus 1. So we factor out the GCF in the top. The bottom doesn't have a GCF because this one doesn't have an x, but it is dots. Good old difference of 2 squares. Because the first is a squared, it's 2x being squared makes 4x squared. And then 1 is just 1 squared. So dots means we take the first piece squared minus the second piece that's squared, so 2x minus 1, and then we flip it to plus. And so if you need convincing, you can always multiply this out and see that it would give us 4x squared minus 1, because alternating plus and minus makes that middle term cancel. All right, well, speaking of canceling, now after it's factored, now we can reduce. So we can reduce the fraction, meaning cancel, if there's matching factors. And I'm underlining factors again because it's really important. We don't want to just say, oh, look, there's an x here and an x here, those cancel. That doesn't work. But if an entire factor, a piece being multiplied, matches in the top and bottom, then we can cancel. So what we get after it's reduced is x over 2x plus 1, right? Because the factors Those are the remaining factors after we cancel. But because we canceled and because it's a complex fraction, we need domain restrictions. So domain restrictions for any canceled factors and based on the original problem. So the factor that canceled is 2x minus 1. I need to set that equal to 0 because I can't divide by 0. So I would add 1, divide by 2. So 2x equals 1, x equals 1/2. So that's our first domain restriction. X cannot equal 1/2. And our second domain restriction comes from the original problem. I can't divide by 0 here as well. So this x cannot equal 0. So that's the other domain restriction, is that x cannot equal 0. And x squared equals 0 is also x equals 0. So it's a lot. Hopefully these steps make sense. Let's try it again using the same steps. All right, second example, and I'll try to keep my steps visible here. Simplify. All right, so first step, multiply all numerators, all 4 pieces, and again, if it helps, make the 2 over 1. It can be a fraction too. We're gonna multiply the tops of all 4 of these fractions by whatever will get rid of all the bottoms. So in this case, if I wanna get rid of the 1, it doesn't matter, but I wanna get rid of both the x minus 1 and the x. So that's what we're gonna multiply by. X times x minus 1. X times x minus 1. Because that will get rid of both denominators that I'm seeing. So we're multiplying the tops of every fraction in this problem by that least common denominator. All right, so let's see what we get. So I'm multiplying the top, and I'm just going to write it out. 3x times x minus 1 over x minus 1 plus 2x times x minus 1. I guess I didn't need the over 1, but it's there, so we're going with it. Bottom, 1x times x minus 1 over x minus 1. Oops. And then minus 1x times x minus 1 over x. All right. Other than my little mess up there, we seen how all I did was multiply the top of every fraction. That's it, by that LCD. But the reason we did that is because now every single mini denominator within this bigger fraction should cancel. X minus 1's cancel. The one I wasn't worried about anyways. X minus 1 cancels. This x cancels. So let's see what we got now. In this next step, there shouldn't be any fractions except for the one main one. So here the x minus 1's went away, or divided to 1. So we're left with 3x. Here, dividing by 1 doesn't do anything. So we just have plus 2x times x minus 1. On the bottom, 1 times x, well, that's just x, minus, and I'm going to leave this 1 here because I'm going to have to distribute this minus sign to the parentheses. And that's a really common issue, right? Is that if you have a subtraction, after you cancel, these parentheses need to stick around until we distribute that negative sign. So we're going to definitely need to distribute that negative sign, and that's something to look out for when we're trying these on our own. All right, so I'm going to distribute the negative 1. I'm also going to distribute this 2x because now we're on step 2. Simplify the top and the bottom, and then if we can, factor them. So first we're on simplify. And notice I'm not canceling anything, right? We can't do that until the numerator and the denominator are separately simplified. All right, so the top, 3x plus 2x squared minus 2x. I'm just distributing. The bottom, x minus x plus 1, because a negative times a negative makes a positive. And now we're still on simplify, so we see what reduces, what simplifies. Let's see, positive x minus x, well, those go away. And then 3x minus 2x is just 1x. So the top, I'm just going to write it out here. I'm going to put the x squared first. That just feels right to me to put it in more standard form where the bigger exponents come first. So 2x squared is there, but then 3x minus 2x makes plus 1x. And the bottom is just 1. So we don't even need the bottom there in our final answer. And, you know, we like to factor, so I'm going to factor out the GCF. So this is going to be equal to x times 2x plus 1. But really, since nothing's canceling, it's not a big deal if you left it unfactored. But we don't want to write it over 1. If you end up with just 1 on the bottom, we can get rid of it. If you end up with just 1 on the top, that is very important to leave it there, because that, you know, that makes it a fraction still. All right, well, let's see, we didn't cancel any factors, right? So we don't have any domain restrictions from canceling factors, but we should look at the original problem still for domain restrictions. In the original problem, we have an x minus 1 in a denominator, so that can't equal 0, which makes x can't equal 1 if I add 1 to the other side. And we also just have a plain old x in the denominator, so we can't have x be 0 either. So from those two denominators, we have two domain restrictions. So I'm putting comma, and then our domain restrictions are x cannot equal 0 or 1.